Okay, this mini lecture is going to focus on the protecting group section of chapter 21, which again is nice because it's a little bit of review of the carboxylic acid derivative chemistry we've been studying, plus a little bit of review regarding protecting groups. So, revisiting protecting groups. Remember, you are doing this because you have to. There's something that's going to interfere with a subsequent step in your synthesis. So since you have to do this, you have to find a protecting group that will be easy to put on in a nice high yield, easy to take off in a nice high yield, but it invariably means two more reactions, which will take more time and reduce the overall yield of your synthesis. So you want to avoid them like the plague. Review. We know how to protect alcohols to take care of that darn pesky acidic hydrogen, which is going to interfere. For example, if I'm trying to make a Grignard, I can't have that acidic hydrogen there. So by making a silyl ether, since the oxygen-silicon bond is so strong, that's an easy to put on and an easy to take off protecting group, because the fluoride silicon bond is even stronger than the fluoride oxygen bond. You can also protect alcohols with that crazy DHP. That's called a pyranyl ether because that's a pyran. Again, note the key offender, the acidic hydrogen, is gone. In both cases I've made an ether. Ethers are pretty inert. How do I deprotect my pyranyl ether, my THP ether? By using water and acid, because look, it's an acetal. We can protect aldehydes and ketones. Why would we have to protect aldehydes and ketones? Well, because these are excellent electrophiles. So if I have to add a Grignard, for example, to someplace else in the molecule and I don't want it to go here, I have to mask that. How can I mask that? By the acetal. And again, the acetal is deprotected by acid and water in a hydrolysis mechanism. So what about our new functional groups, carboxylic acids and their derivatives? Well, let's say we want to do this reaction. Let's say I would like to maybe I would like to try and do an SN2 here, or maybe I want to make an amide here. Okay, we know that's not going to work. Why is it not going to work? Because the only thing that crazy amine is going to do is deprotonate my carboxylic acid. So if I wanted to actually go and do an SN2 on the carbon bearing the bromine, well, I'm going to have to figure out a way to protect the carboxylic acid temporarily in a high yielding reaction. So the best way to do that is to make an ester. Not just any ester. This BN stands for benzyl, which is this guy. So what I want to do is make the ester, the benzyl ester from this carboxylic acid. How do I do that? Well, the best way to do it is activate it, and again, the way you know how to activate it is by adding thionyl chloride, and then add benzyl alcohol. So that should work lickety-split to give you the benzyl ester, and then I can carry out my substitution reaction no problem, get my desired product. Now all I have to do is deprotect, and the nice thing about the benzyl ester, it's extremely reactive to deprotection by hydrogenation, which is kind of interesting. But yeah, this is a very easy deprotection step, often quantitative, often 100% yield. So the benzyl ester is a great protecting group for carboxylic acids. Just a quick note, in table 21.2 of your textbook, it refers to this protecting group as BZ. It is not BZ. BZ is this guy. So you might want to make a note of that. If you see BZ, this is what it looks like. BN, again, is the CH2 pH. Alright, well, amines can be problems too. They can be problems in terms of an acidic hydrogen. They can also be problematic in that they're electron rich. So they are potentially competing nucleophiles, and they're potentially competing things that can be oxidized. So for example, if I want to oxidize that double bond and make this epoxide, well, it turns out I will also oxidize my amine, which I do not want to do, because once you've oxidized your amine to an amine oxide, that's a pain. So you don't want to go there. What do I do? Well, it's basically the same sort of thing. I can convert my amine to a carboxylic acid derivative. So add acetyl chloride. Now I can do my up, down, out and put the acetyl group on my amine. The offending hydrogen is gone. I've definitely reduced my nucleophilicity because the lone pair is now tied up in that resonance delocalization. And so, easy peasy, I've protected my amine, and to deprotect, I just need to hydrolyze off my acetyl group, H2O and H+. And then, of course, there's Bock. Bock is a very, very popular protecting group. You'll see it all over the place. It stands for butoxycarbonyl, BOC. And this is a picture of the Bock anhydride. Remember that anhydrides, like chlorides, are right up at the top of the reactivity ladder. So this can react readily with amines, as in this example. So this is from the recent literature. Basically, these researchers are looking to make something that has good anti-cancer promise, and to do that they started with this guy, which they want to, if you look over here, look at their target over here, you can see they want to do nucleophilic substitution on the nitrogen on the right. But as you can also see, we have two competing nitrogens, this one and this one. So they're not going to bother with trying to finesse this. They go ahead and protect the nitrogen here with the butoxycarbonyl protecting group. Then they can carry out substitution reaction, and all is well. Now here's the reality of that reaction, and it's a good experience for you to see the difference between what we write about in a textbook and what we do in the lab. So this is the experimental procedure for putting that Bock group on. And I just want to highlight a few things. So first of all, I can highlight the god-awful nomenclature, which, you know, actually you've learned all the nomenclature rules, and at some point in your career you could actually name this thing. Don't worry, it won't be on the final. Alright, so things to point out. Here is my reagent. Here is the tryptophan derivative, the dinitrogen thing that we were looking at, that they're adding it to. But also note that there's all kinds of other things in here. They have another base. They actually have two additional bases. So it's complicated. Here's my solvent. It tells you how much I'm going to use. I have to do this slowly for 30 minutes at 0 degrees just to get that first stuff mixed up together. Then I add my amine, another 30 minutes, and so on and so forth. It takes a long time. They use TLC to know when it's done. Then they work it up by a whole bunch of stuff. Now notice, you saw how that reaction was written down in the previous slide. We don't include all this stuff, but this is the reality of carrying this out in lab. The workup means adding water, adding salt water, then since there's ether in there, we're adding a drying agent, then we chromatograph it to purify it, and then here's the good stuff that proves that we made our product. And so that's a really good review of all kinds of organic chemistry, from lecture to lab to NMR. And then, did you hear about the wedding between two antennas that fell in love? Yeah, the wedding was awful, but the reception was great. See ya in class.